Hi, this is Mr. Heineman from Evergreen High School. This is for my Algebra 1 classes. This is standard 4.2, Solving Systems of Inequalities. So systems of inequalities are at least two inequalities that use the same variable. So they're basically like systems of equations, but we use inequalities instead. And the inequalities can come in the same forms as equations. We're going to be using techniques that we learned in Unit 3 with inequalities to solve systems of inequalities. So a solution to a system of equations, or a system of inequalities I should say, is a point that makes both inequalities true. That means that because inequalities, as we learned in Unit 3 from Standard 3.2, because inequalities have many possible solutions, and they're graphed using half planes, a system of inequalities is also going to have many possible solutions. It also means that the only way that we can solve is by graphing both of them on the same set of axes. And then when we graph them, we have two half planes, and the solution set is going to be the overlapping of the two half planes. And we'll see that when we actually go to graph them. But as always, we'll start by looking at possible solutions and whether or not they are actual solutions of systems of inequalities. So when it comes to systems of inequalities, we can see over here that the graph has two boundary lines for the inequalities, but only one shaded area. That's because, as I said, the half planes for this inequality and this inequality overlap here. So normally this inequality would have this whole side over here, including this area up here, shaded, and this inequality would have everything down here shaded, including this area. But because this area is the one that both of them would have shaded, this is where all the solutions to the system will be. So when I plot each of these points, I'm going to see if they're in the shaded area or not. On the line will work for this solid line, but not for the dashed line. Dashed line means those don't qualify as solutions. Dotted line means they do. Or I'm sorry, solid line means they do. So now plotting these points, if I go to -5, 3, that one is in the shaded area, so it is a solution. So I'm going to circle it to remind myself. For B, 1, -2 appears to not be a solution. 0, -4 is down here, also not a solution. -8, -1 be right here. It would be a solution. So the solutions are A and D because, and it's as simple as saying, because they're in the shaded area. So that's all that is required in terms of solving systems or solutions to systems, is just to look and see if points are in the shaded area. And that's perfectly acceptable mathematical reasoning to say that they are solutions because they're in the shaded area. In addition to determining if points are systems, we should also be able to determine from a graph what system we're looking at. And usually when we have problems like this, our focus is really just on these inequality symbols. That's almost always what they're testing. So they're not testing on slope and intercept, except that we need to know which one is which so we know if, well, we know where the shading is supposed to be. So both of them have an intercept of -6, which is apparent by all of the inequalities. They just have different slopes. This one has a positive slope. In fact, it's +3 because it goes up 6 and over 2, which is an average of 3, up 3 over 1. So it's a positive 3. The other one looks like it's a down 2 over 2, which is a negative 1 slope. So this vertical one here is, in our inequality stack, it's the second one. And then this one here is the first. So when we look at this one, we are below this one. And this, for this one, the shading is above. So what that means is that for this inequality, that means we're looking at less than, and for this one, it's going to be greater than. So we find the combination where the negative slope is greater than and the positive slope is less than. We look at the lines, we notice both of them are dotted, which means that neither one is equal to. We also see that none of these options are equal to, which makes it easier on us. We're just looking at direction now. So I'm looking for above for the negative slope and below for the, or greater than for the negative slope and less than for the positive slope. And that looks like it's this one here, C. And it's C because the one with the positive slope is shaded below. And the one with negative slope is shaded above. And again, these are both, this is like an acceptable reason because it's using what we know about slopes, and you're differentiating between the two using a general idea of slope, even if it's not specific slopes. And the idea that shading above or below, this is when it was above, wasn't it? Relates back to the inequality symbol, that above always means greater than and below means less than. So now we're going to graph our own systems of inequalities. So as I said earlier, the only way we can solve systems of inequalities is by graphing. And so when we look at graphing systems of inequalities, it's really just graphing two inequalities one at a time. There's slight differences, but we can think of it as just like we've got two inequalities, let's graph both of them. So whenever we graph inequalities, we should find 2 points. And in slope-intercept form, we can use the y-intercept and the slope to find 2 points. The y-intercept is automatically 1 point, then you can use the slope to find a second. In standard form, we can take turns setting x and y to 0 and then solve for each intercept. So we do it once by setting y to 0 to find the x-intercept, and then set x to 0 to find the y-intercept. Plot both those points. Once we've got those points, then we can draw our boundary lines. The boundary lines for any inequality are either dashed or solid. Dashed means not equal to, solid means equal to. That's easy enough to do. Then we would shade the correct overlapping region. Greater than always means above that line, less than works below the line, and the shading has to work for both inequalities. And we'll see what we're talking about visually next. We also need to be aware of certain situations when it comes to standard form that might change how our inequalities are graphed. And we'll talk about that when we come to that. So when it comes to graphing this system, both inequalities are in slope-intercept form. So it's as simple as finding each one's intercept, using the slope to find a second point, and then we can draw our boundary lines. So we're going to find, I'm going to do these one at a time. So first we'll find the first one. Remember, intercept is always what's not with x, and then slope is always what's next to x. So in this case, the y-intercept is 1, and then the slope is -2, so I'm going to count down 2 and to the right 1. So our first inequality is there, and then I look at the inequality symbol and it's a not equal to, so I'm going to draw a dashed line. Okay, and then for this one, the y-intercept is -3, the slope is +2, so -3 here, +2 actually puts me at the same point that I used for my first one. Okay, and I notice it's also a not equal to, so it's also going to get a dashed line. Now that I have my lines, I can shade my boundary or my regions depending on what the inequality symbols are. Now, keep in mind that we're eventually only going to shade an overlapping region, but at first we can shade both of them. So for this inequality, which was this line, it's greater than, so we would shade above. So I could shade above, and then for this one it's less than, so I would shade below that. So when I shade below that, we see this overlapping region here. And since this is the overlapping region, that's really the only one we need to shade. So in the future, we'll just plan on shading that one. And that's how our inequality graph should look like. So our system of inequalities should have a single part of the graph shaded. If we look at the two lines, kind of divides it into 4 parts. We're just going to use our inequalities to figure out which of the 4 parts should be shaded. So in this case, because it's got to be above this line and below this line, that's the only one that fits the bill. And we'll get more into that as we get into future systems here. So with this one, this is a system that has 2 standard form equations. With this one, we're just going to use the intercepts to graph, and then we're going to shade. So in this case, we're going to have to do some work to find the intercept. So we kind of treat it like an equation first. So for this first one, if we set y to 0, 6x would be 6, which means that x would be 1, well, -1 for that one. So the x-intercept is -1. The y-intercept, we treat it like an equation again, setting x to 0 this time, so y would be 2. So I would connect those dots, and of course go all the way through. In this case, we look here and we notice not equal to, so now we're going to draw a dashed line there. With the second inequality, again, set y to 0 first. X is 2 in this case, so we're going to plot a point here at 2 on the x-axis, and y equals -10 for the y-intercept. Divide by 10, y is -1. So now here's the intercept for that. And then when I draw this one, though, I see that this is an equal to, and so it's going to be a solid line. And because it's going to be a solid line, I draw my solid line in there. So now I've got 4 sections that could be where my shading is. I need to figure out which of the 4. And what's nice is as I go through this, I will eliminate half my possibilities each time. So because I'll eliminate half my possibilities, it makes it two steps, and I'll figure out which one I need. So when it comes to this first one, which I know is the dotted line because it's the not equal to, that is less than, so I got to shade below that. So it's either this section or this section. And I could mark these, like 1, 2, 3, 4, so that I know which ones they could be. So I know it's not 1, and I know it's not 4. It's got to be 2 or 3. For this one, it's got to be above this line, which means it can't be 3, and it must be 2. So I would shade this little area in here as the solution set for this system. So graphing inequalities can be tricky sometimes. And this is a situation where it can get tricky. This inequality has a negative sign in front of the 4. In front of the 4y. And that's significant because if we were to solve this inequality 4y to make it a slope-intercept form inequality, we remember that when I divide by a negative number, that causes a flip of the inequality, which means that even though, or this is 2x, tell you what, let's erase. Okay, maybe that'll help. Now we'll go back to my pen. So there we go. So what that means is that even though this inequality would be graphed using this, and our other inequality, we could figure out the two intercepts. X-intercept would be 3, and then y-intercept would be 6. Okay. So I could plot both those, and we notice that both of them are not equal to, so both of them are going to be dashed lines. But when I go to do the shading, that's where it gets tricky. And because this negative sign, this negative symbol is here, it's going to actually be shaded the opposite of what this is. So this shading would be below because this is positive. So this is that line. So we'd be below this line. So if we number these again, right, it's not going to be 1 and it's not going to be 2 because it's got to be below that line. And normally we would do above this line, which would be 4. But because of that negative symbol in front of the 4, in front of the 4y, the inequality symbol would flip if we solved for y to get a slope-intercept form inequality, which means that instead of being 4, it's going to be 3. So that's actually where my shading's going to go. So the rule that we can think of is if there's a negative in front of the coefficient of y, then we shade opposite whatever the symbol is. And that's actually a rule we can use because it'll work every time. So if there's a negative value for the coefficient of y, then you're going to essentially flip the symbol and treat it like you flipped the symbol. You could, if you wanted to, reinforce that by multiplying by -1, which would do the same thing. Since you're multiplying by a negative number, you'd get the same intercepts, but then you'd have a flipped symbol. So that would be the new inequality that you would use. And you could do that, and that might help you with graphing this. But remember, when it comes to negative coefficients of y in standard form inequalities, you gotta treat the symbol as if it were flipped and shade opposite what the symbol says. So writing systems of inequalities are the same. It's just that sometimes they don't expressly tell you about each inequality. So the first thing I'm going to do is go through, and I'm always going to annotate my story to see what information I can get from it. So it says he's going to order some salmon and rockfish for a seafood soup at his restaurant. He wants to buy less, and it seems like an important word, right? Less than 18 pounds of fish. And I see a number, I see a unit, and then I also see like what we're talking about. So 18 pounds of fish. It tells us that rockfish cost $5 per pound. I include that. That sounds like a rate of change. And salmon cost $13 per pound. So, and he wants to spend at most $130 on seafood. And it also tells us that X is going to be rockfish and Y will be salmon, which makes our life easier because I don't have to decide that. It's something that's decided for me. Well, there's 4 numbers here, and what might be confusing is that we need 2 systems, and if you only took into account numbers, then you might think that there's 2 systems of equations here, or there's 2 slope-intercept inequalities, rather. The reality is there are 2 standard form inequalities here, and it's just difficult to pick out because of the way it's worded. The one that seems obvious is the second one. Rockfish cost $5 per pound, salmon costs $13 per pound, and he wants to spend at most $130. Since those all have the same unit, dollars, that should be in one inequality. And so that's going to be $5 per pound of rockfish times the number of pounds of rockfish plus $13 times the number of pounds of salmon, and that should be at most 130. And we can start with an equation, but at most, remember, at most would be 130 would be the absolute highest amount I could pay. I would pay. If that's the absolute highest amount, then first of all, I'm going to erase this. And instead, I'm going to write in, if it's at most, then it has to be 130 or less. So this has to be less than, or it could be equal to, 130. So if he wants to spend at most, that's always less than or equal to. The other one is really contained all in here. We say he wants to buy less than 18 pounds of fish. And when he uses just the word fish, that tells me that it's both rockfish and salmon, because those are both fish. And so it's really simply adding the 2 amounts of fish, pounds of rockfish plus pounds of salmon. And we want that to be less than, which is straightforward. Less than symbol, 18. There's my solution, or there's my system of inequalities. And then I could go in and write that, or graph that, find the overlap, and those would be my possible solutions to this system. So when it comes to systems of inequalities, sometimes it's not quite clear where each one is, but if you can pick out things like this, when it says pounds of fish, well, that means that rockfish and salmon are together. That's a sum of those 2. That has to be less than 18. Then we just add the 2 variables. If there's other rates of change included, like this, then we use those rates of change as coefficients of each variable, and then whatever our total has to be constrained by. So that's it for 4.2. That's it for semester 1. Good luck on the final.